Hi, I am Gangadhar, lecturer in mathematics from Giraj Government College, so Department of Mathematics. Today topic BSc third year. So in the linear algebra, coordinate of vectors, the topic. So before going the topic, so we learn one theorem. So that theorem is the unique representation theorem. So the theorem statement, let P equal to B1, B2, so on Bn be a basis for a vector space V. Then then for each x in V, there exists a unique set of scalars C1, C2, so on Cn, such that x equal to C1 B1 plus C2 B2 plus so on plus Cn Bn. So the vector x can be expressed as linear combination of the vectors B1, B2, so on Bn in unique way. So proof of the theorem. So first B equal to B1, B2, so on Bn is basis for a vector space. So basis means B is linear independent and V equal to span B. So we will take one vector from x from B. So one vector x from B. So x is linear combination of the elements of B, B1, B2, so on Bn. So we will write x equal to C1 B1 plus C2 B2 plus so on plus Cn Bn. Next we will take another vector in V, and we know V equal to span of B. Span of B means x is also linear combination of the elements of B. So x value d1 b1 plus d2 b2 plus so on plus dn bn. So here we define two x values. One is c1 b1 plus c2 b2 so on plus cn bn. Another one is d1 b1 plus d2 b2 plus so on plus dn bn. So here we subtract each from another. So x minus x equal to c1 minus d1 into b1 plus c2 minus d2 into b2 plus so on plus cn minus dn into bn equal to 0. So but here b is linear independent because it is basis. So b is linear independent means in the linear combination all scalar values are zeros. So that is c1 minus d1 equals 0, c2 minus d2 equals 0, so on, cn minus dn equals 0. So that is c1 equal d1, comma c2 equal to d2, so on, cn equal to dn. So in the both the linear combinations, all scalar values are equal. All scalar values are equal means the representation of x of linear combination of b1, b2, so on bn is unique representation. So therefore, for each x in V, there exists a unique set of scalars c1, c2, so on cn, such that x equal to c1 b1 plus c2 b2 plus so on plus cn bn. So now the definition is coordinates. So suppose b equal to b1 b2 so on bn is a basis for a vector space V and x is in V. The coordinates of x relative to the basis B are the scalars c1, c2, so on cn, such that x equal to c1 b1 plus c2 b2 plus so on plus cn bn. So in this case, the vector in r to the power n x from B we write to c1, c2, so on cn is called the coordinate vector of x relative to B. So here coordinates means, so given x vector we write a linear combination of the elements of basis. In that linear combination, getting scalar values form one vector. That vector is called coordinate vector. So x equal to c1 b1 plus c2 b2 plus so on cn bn. Here c1 c2 so on cn are scalar values. These scalar values form one vector. That vector is called the coordinate vector of x relative to the basis b. So it is denoted by x from B. So now we will see one example. So consider a basis B equal to B1, B2 for R2, where B1 equal to 1, 0 and B2 equal to 1, 2. Suppose an x in R2 has the coordinate vector x from B equal to minus 2, 3. Find a x. So here x from B coordinate vector is given, so we want x value. Means x is the linear combination of the elements of B. So x is the linear combination of the elements of B. So using scalar values, C1, C2 values are given minus 2, 3. So here x equal to x equal to C1 B1 plus C2 B2. C1 value minus 2, C2 value 3. B1 B2 values are given 1, 0, 1, 2. So now minus 2 into 1, 0 plus 3 into 1, 2, that equal to we get 1, 6. So it is the vector x. So now the next problem. So find the x determined by the given coordinate vector x from B and the given basis B. So here also same in the previous problem. So here x from B matrix is given. So two basis values are given. We want the vector x. So here x equal to x is the linear combination of the x equal to x is the linear combination of the vectors B, C1 B1 plus C2 B2. Here C1 C2 values are given in the first problem 5 3 and B1 B2 vectors are given 3 minus 5 minus 4 6. X equal to C1 B1 plus C2 B2. Where here we write the values 5 into 3 minus 5 plus 3 into minus 4 6. So we get result value 3 minus 7. So it is the vector x. In the second problem, C1 C2 values are minus 2. So same way. So here remaining problems. So in the next problem, so the entire in the vector x 1 6 are the coordinates of x relative to the standard basis epsilon b equal to e1 e2. So here we find x value. So 1 6 equal to standard basis of R2. Standard basis of R2 means e1 e2. Values are 1 0 comma 0 1. So here 1 into 1 0 plus 6 into 0 1, that equal to we get. So 1 6, 1 into e1 plus 6 into e2. So here the x value is 1 6. If the given basis is standard basis, then coordinate vector of the given vector is the same vector. So now the next problem. So let b1 equal to 2 1, b2 equal to minus 1 1, x equal to 4 5, and b equal to b1 b2. Find the coordinate vector x from b of x relative to the basis b. So here coordinate vector means x value we write in the linear combination of the vectors b1 b2. So x equal to c1 b1 plus c2 b2. We write linear combination c1 into 2 1 plus c2 into minus 1 1 equal to x vector 4 5. So here we get the equations 2c1 minus c2 equal to 4, c1 plus c2 equal to 5. So here solving of non-homogeneous equation, that is ax equal to b form. In that, so box AB matrix is called so we write a box AB matrix. That matrix is called augmented matrix. So that augmented matrix is reduced to upper triangular form, and again we write the equations. Those equations are solved for given variables. So here the equations we write in matrix form, that form is ax equal to b form. So X equal to B form. So box AB reduced to upper triangular form. Again we write the equations. So those equations are solved for C1, C2 variables. And here we get the values are C1 equal to 3, comma C2 equal to 2. So X equal to 3B1 plus 2B2. So coordinate vector is X from B equal to C1, C2, that equal to 3, 2. So now the next problems are same model problems. So here find the coordinate vector X from B of X relative to the given basis B1, B2, so on Bn. B1, B2 values are given, X vector is given. So we want so the matrix B1, B2 of X. So now here we write B1, B2, X, B1, B2, X, 1 minus 2, 3 minus 5 minus 1, 1. So this matrix reduced to upper triangular form. So we get the form is 1, 0, 8, 0, 1 minus 5. So here solution. So X from B matrix is 8 minus 5. Same way next one. So here see the seventh one. So 3 vectors are given. 1 minus 1 minus 3. Minus 3, 4, 9. So B3 third vector 2 minus 2, 4, and last vector so 1, 8 minus 9, 6. 8 minus 9, 6. So here these values we write in matrix form B1, B2, B3 and X. That matrix is reduced to upper triangular form by using row operations. Then getting matrix is obtaining matrix 1, 0, 0 minus 1, 0, 1, 0 minus 1, 0, 0, 1, 3. So here coordinate vector is last column elements are coordinate vector elements X from B matrix minus 1, 3. Same way 8th problem. So next one example here. So in this example, so let P be the standard basis of vector space P3 of polynomials. So let B equal to 1t, t square, t cube. It is a standard basis of third degree polynomial, and general form is P of t equal to a0 plus a1t plus a2t square plus a3t cube. So we want a, so it is a standard basis. Standard basis means, so we direct to P from B matrix, we write coefficients of the polynomial, constant value a0, t coefficient a1, t square coefficient a2, t cube coefficient a3. It is the, if the given basis is standard basis, then coordinate vector of the given vector is the same vector. Next problem. So use coordinate vectors to verify that the polynomial, so 1 plus 2t square, 4 plus t plus 5t square and 3 plus 2t are linear independent in P2. So show that these polynomials are linear independent in P2. Means we write a coefficient matrix. What is the coefficient matrix here? Constant t coefficient, and t square coefficient. So we write in the first vector coefficients are constant is 1, t coefficient is 0, column way we write t square coefficient is 2. In the next vector constant 4, t coefficient 1, t square coefficient 5. In the third vector, so constant 3 and t coefficient 2, t square coefficient 0. So this matrix is reduced to upper triangular form. So getting the form is 1, 4, 3, 0, 1, 2, 0, 0, 2. Here we get two pivot columns. So here we get first column and second column are two pivot columns. So third column is the linear combination of first and second. Third is the linear combination of first and second, means given vectors are direct, we say that linear dependent. In the given vectors, one vector is the linear combination of the remaining, then we say that given vectors are linear dependent. So in the given vectors, any one vector cannot be linear combination of the remaining, then we say that given vectors are linear independent. So here third vector is the linear combination of the first and second, means given vectors are linear dependent, not independent. So next example, let v1 equal to 362, v2 equal to -101, and x equal to 312, so and b equal to v1 v2. So then b is a basis for h, h value is span of v1 v2. Determine if x in h, and if it is, find the coordinate vector of x relative to b. So x value we write linear combination of the vectors v1 v2. So here x value we write linear combination of the vectors v1 v2. So c1 into v1 plus c2 into v2 equal to x value. So these three vectors we write in single form, that is ax equal to b form. In the ax equal to b, so box AB we write box AB means 3 minus 1 3, 6 0 12, 2 1 7. So this box AB matrix is reduced to upper triangular form. Then resulting matrix gives the constant values or scalar values c1 c2. So upper triangular form is 1 0 2 0 1 3 0 0 1. So last column elements gives the c1 c2 values. c2 is 2 and c1 is 2, c2 is 3. So therefore, so coordinate matrix is 2 3. So now the next problem. So find the change of coordinate matrix from B to the standard basis of R to the power n. Standard basis of B to the standard basis of R to the power n. So B equal to 1 minus 3, 2 minus 5 is given. So here we want coordinate change of coordinate values. So the change of coordinate matrix from B to the standard basis in R to the same matrix. Here we get B equal to B1 B2. So B1 value 2 minus 9 and B2 value 1 8 we get. So same way they change value 3 to 8 minus 1 0 minus 2 and 4 minus 5 7. So in the next problem, so find the inverse matrix of x from B for the given x and B. So B equal to 1 minus 2 minus 3 5, x equal to 2 minus 5. First here we find P from B. P from B means coordinate matrix of x with respect to the basis B. Coordinate matrix of x with respect to the basis B we find. So P we find P from B matrix. So that matrix x from B equal to PB inverse into x. Here we get PB inverse. So PB inverse matrix is 3 minus 4 minus 5 6 into 2 minus 6. So that equal to we get 6 4 x from B matrix. So use an inverse matrix to find x from B here. So x from B, use inverse method means, so PB x equal to P from B into x from B. Definition, x equal to P from B into x from B. So x from B equal to PB inverse into x. PB inverse into x. We find P from B means coordinate vector of x with respect to the basis B. So we get the matrix. So P inverse matrix we get 3 minus 4 minus 5 6 into x. Then we get coordinate vector x from B, 6, 4. Same way, next one. Now the problem, the set B equal to 1 plus t square, comma t plus t square plus 1 plus 2t plus t square is basis for P2. P2 means second order polynomial. Find the coordinate vector of P of t equal to 1 plus 4t plus 7t square relative to B. So coordinate vector means given vector we write linear combination of the elements of the basis. So that is 1 plus 4t plus 7t square equal to C1 into 1 plus t square plus C2 into 1 plus t square plus C3 into 1 plus 2t square. So C1 into 1 plus t square plus C2 into t plus t square plus C3 into 1 plus 2t plus t square. So equal to vector P of t 1 plus 4t plus 7t square. So we compare both side coefficients. First constant values C1 plus C3 equal to 1. T coefficients C2 plus 2C3 equal to 4. T square coefficients C1 plus C2 plus C3 equal to 7. So this here we write given equations in matrix form Ax equal to B form. In that box AB matrix is augmented matrix. So that matrix is 1 0 1 1 0 1 2 4 1 1 1 7. So that matrix is reduced to upper triangular form. Reduced to upper triangular form, or this form is called Gauss-Jordan form. Here the form, so unit matrix into one vector equal is, that form is called I comma B form. We say that I comma B form. So that form is called in Gauss-Jordan. So the Ax equal to B matrix, box AB matrix is reduced to upper triangular form, and again we write equations. Those equations are solved for given variables. So here we get the form in the here we apply Gauss-Jordan method. So matrix A is reduced to unit matrix form. Same operations we will take in matrix B. Here we getting the matrix is 1 0 0 2 0 1 0 6 0 0 1 minus 1. So here P from B matrix is 2 6 minus 1. So box AB matrix is reduced to 1 0 0 alpha 0 1 0 beta 0 0 1 gamma. Then solutions are alpha beta gamma. So here alpha beta gamma solutions 2 6 minus 1. These values form vector. That vector is called coordinate vector of P with respect to the basis B. So next same model problem. So the set B equal to 1 minus t square t comma t square comma 2 minus 2t plus t square, P of t 1 plus 3t minus 6t square relative to the basis B. So first P of t we write linear combination of the vectors, given vectors C1 V1 plus C2 V2 plus C3 V3. So we write equations. Those equations we write in matrix form. So in the matrix form, so Ax equal to B form we get. So box AB, so matrix, box AB matrix is reduced to upper triangular form. Again we write equations. Those equations are solved for given variables. It is the one method. Or box AB matrix is reduced to the form 1 0 0 alpha 0 1 0 beta 0 0 1 gamma. Then solutions are alpha beta gamma. So here box AB matrix is reduced to upper triangular form. So here the form is minus 1 minus 1 1 minus 6 0 1 minus 1 3 0 0 2 minus 2. Again we write the equations. So those equations are 2x3 equal to minus 2. Next one, x2 minus x3 equal to 3. x2 plus 1 equal to 3. x2 equal to 2. We get minus x1 minus x2 plus x3 equal to minus 6. Then we get x1 value. So here x1 3, x2 2 and x3 value minus 1. So P from B matrix is 3 2 minus 1. So the next problem, let vector v1 equal to 1 minus 3, 2 minus 8, v3 equal to minus 3 7 span R2, but do not form basis. Find two different ways to express 1 1 as linear combination of v1 v2 v3. So first, do not form basis. So do not form basis means first here we find the linear combination. In the linear combination, using scalar values are exist or not. So we must solve the vector space vector equation x1 into 1 x1 v1 plus x2 v2 plus x3 v3 equal to, express the vector means that equal to x vector. So x equal to, we write a linear combination of the vectors v1 v2 v3. So 1 1 x into 1 minus 3 plus x2 into 2 minus 8 plus x3 into minus 3 7. So here it is the form Ax equal to B form. We write the box AB matrix. So box AB matrix is 1 2 minus 3 1. So minus 3 minus 8 7 1. So that matrix reduced to upper triangular form. Again we write equations. So those equations are solved for given variables, and we getting the equations x1 minus 5x3 equal to 5, one equation. Next one, x2 plus x3 equal to minus 2. So here we get x1 x2 values. So and we get x3 value is not there, so we say that is 0. So here, so produce two different ways to express 1 1 as linear combination of the vectors means, so 5v1 minus 2v2 and 10v1 minus 3v2 plus v3. So there are infinite many correct answers to this solving problem. So because here x1 equal to 5 plus 5 x3 and x2 equal to minus 2 minus x3. So means x3 is independent value. So x3 is variable. x3 is any variable means any real number. So for different values of x3 we get x1, x2 values are different. So x is any real number means, so x is infinite, x3 is infinite. So same way we get the solutions are also infinite solutions. So next one practical problem is there, so that one do over. So now the next topic is change of basis. Change of basis. So its definition is, change of basis definition is, let b equal to b1 b2 so on bn, c equal to c1 c2 so on cn, b basis of vector space B. So then there is a unique n by n matrix p from b to c such that x from c equal to p from p to c into x from p. So x from c equal to p from b to c into x from b. So p from b to c is called a coordinate vector from the basis b to c. P from b to c is called coordinate vector from the basis b to c. So the columns of p from b to c are the c coordinate vectors of the vector in the basis p. So that is p from b to c equal to b1 of c, b2 of c, bn of c. b1 of c means it is coordinate vector with respect to the basis c. Same way b2 of c also, bn of c also. So the matrix P from B2 to C is called the change of coordinate matrix from B to C, and here x from B. So x from B definition is P from B to C whole inverse into x from C. X from C definition P from B to C into x from B, and x from B definition is P from B to C whole inverse into x from C. So here change of basis in R to the power n. Standard basis. In the standard, if the given basis is standard basis, then coordinate vector of the given basis is the same basis. So here example, consider two bases b1 equal to b1 comma b2 and c equal to c1 comma c2 for a vector space v2 such that b1 equal to 4c1 plus c2 and b2 equal to minus 6 1 plus c2. Suppose x equal to 3b1 plus b2. So and x from B matrix 3 1. Find x from C. Find x from C. So here b1 b comma c are two bases of vector space v2, and b1 is linear combination of elements of C. b1 b2 are linear combinations of elements of C. So b1 equal to 4c1 plus c2, b2 equal to minus 6c1 plus c2. So b1 from C matrix 4 1, b2 from C matrix is minus 6 1. So x from B matrix 3 b1 plus b2. So here we want x from C. So x from C equal to P from B to C, into x from B. So P from B to C matrix is b1 of C comma b2 of C. b1 of C 4 1, b2 of C minus 6 1 into x from B 3 1. So x from C matrix is b1 from C, b2 from C into 3 1. So we get the matrix b1 from C 4 1, b2 from C minus 6 1, and x from C equal to P from B2 to C into x from B. So P from B to C matrix 4 minus 6 1 1, x from B matrix 3 1 into we get 6 4. So now the problem. So let b1 equal to minus 9 1, b2 equal to minus 5 minus 1, c1 equal to 1 minus 4, c2 equal to 3 minus 5, and consider the basis of R2 given by b1 b2 are two bases of R2. Find the change of coordinate matrix from B to C. So here first P from B to C we define. P from B to C equal to B1 of C, B2 of C. So B1 of C means B is linear combination of elements of C. Same way B2 also linear combination of elements of C. So C1, C2. So B1, C we say x1, x2, B2, C we say y1, y2. So C1, C2 into x1, x2 equal to B1. C1, C2 into y1, y2 equal to B. Or direct here one definition is given. If we want P from B to C, we write the matrix C1, C2, B1, B2, C1, C2, B1, B2. This C1, C2 is reduced to unit matrix form 1 0 0 0 1. Same operations we will take in B1 and B2 then we get the matrix direct B1 from C and B2 from C. So C1 C2 B1 B2 matrix. So in that the C1 C2 matrix reduced to unit matrix form 1 0 0 1 form. So here B1 B2 values are changed. So 6 minus 5 4 minus 3 we get. So these two values form two vectors, B1 from C vector 6 minus 5, B2 from C vector 4 minus 3. So what is P from B to C vector we want? P from B to C vector we want. So that equal to 6 minus 5, 4 minus 3. So same way next one, B1 1 minus 3, B2 minus 2 4, C1 minus 9 7, C2 minus 5 7. So here B1 B2 are two bases of R2. Find the change of coordinate matrix from C to B and B to C. So we find first B to C to B matrix, C2. So C to B matrix. So C2 by B matrix means C2 B matrix means we write B1 B2 C1 C2. So B1 B2 values reduced to unit matrix 1 0 0 1 form. So same operations we will take in C1 C2. So getting vectors 5 6 and 3 4. So P from C2 B matrix 5 6 3 4. P from C2 B matrix 5 3 6 4. So inverse of this matrix we get P from B to C. So P from B to C equal to P from C to B whole inverse. So A inverse matrix definition 1 by AD minus BC D minus B D minus B minus CA. So 1 by 2 4 minus 3 minus 6 5. So that matrix is P from B to C. So same model, no problems are given. So B1 B2 C1 C2 same find coordinate matrix from B to C and C to B. Thank you. Bye.